last lecture yesterday was about the impact of noise on our signals. And the main point we're trying to make is that when we have noise, we can get errors. And errors at the receiver are bad. A bit error is simply you transmit one bit, the receiver thinks it's the other bit. You transmit one, the receiver thinks because of noise that the received bit is actually 0. That's a bit error. We want to avoid that, and we want to know what factors increase the chance of bit errors. We finished last week. This was one example that we went through. There was another one which I'll show shortly. In this example, we had some scheme that maps bits to levels. In this example, we said, okay, if I want to send the bit 0, so the data bit 0, then I transmit my signal at some level. In this example, it's at high level. Whenever we have a 0, send, let's say, some positive voltage signal. And when I have a bit 1 to transmit a signal at a different level, a low level, say a negative voltage. And the idea is that when the receiver receives a signal, if the level of that received signal is high, it assumes bit 0 was received. If it's low, it assumes bit 1. That mapping, called a signal encoding scheme, there are different approaches. We're just using one as an example, as on the board. Bit 0, we transmit, let's say at level 1, as an example, +1, a high level. And whenever we want to send a bit 1, we transmit at a different level, level 2. Let's say -1. All right, this diagram doesn't show the scale, but let's assume this is -1 and this is +1. Volts, for example. We want to understand what impact noise has on different signals. We finished with this example yesterday where we have first a sinusoid, a simple sinusoid. And we have some noise, and the received signal is the addition of the transmitted signal plus the noise. In fact, there's also attenuation. That is, our transmitted signal varies between -1 and +1. That's the magnitude. With attenuation, it gets weaker. So the received signal varies between -0.5 and +0.5, plus the noise. So add in the noise, and you get this going up and down, but with some variations due to the noise. The point we tried to make yesterday with this one and the second signal, the square wave, is that with the first sine wave signal, because of this spike or impulse of noise here, there's a chance that we get an error at the receiver. Because we're transmitting a low level, we see during this duration we're transmitting it down to -1, but because of this large amount of noise here, if we're transmitting at -1 or -0.5 here, plus this noise, it effectively brings it up. And what's received, although not always, but on average, is a positive value here. And it's possible that the receiver interprets that as the wrong piece of data. This was a low value, say -1, bit 1, but the receiver thinks or looks at what was received and sees, okay, this is high. Maybe on average it's 0.1, it's above 0, and it's closer to level, have I missed a number here, level 1 than level 2. And therefore the receiver would think that what was actually transmitted was a bit 0, when in fact what really was transmitted was a bit 1. So it's possible that we have an error at the receiver here due to the noise. With a different signal but the same amount of noise, because of the shape of the signal in that it's always transmitting during this duration at -1, whereas the sinusoid is sometimes at -0.1, 0.2 and so on, and then -1 and then up again, there's a more chance that with the sinusoid, the noise will change the level, causing an error. With a square wave, there's less chance that the noise will change the level, causing an error. The square wave is better in terms of accuracy, or better in terms of fewer errors at the receiver. So the signal shape has an impact upon the number of errors. That's one important point. Given the same amount of noise, some signals will have more errors than others. And in general, the more bandwidth that we use, the less chance of errors. And maybe the slides illustrate that with, if we go back a few slides, where was it? A long way back. Somewhere, sure. This one. Here we have our ideal signal to be transmitted, but if we use this combination of different sinusoids at different bandwidths, this is what's actually transmitted. Bandwidth of 4,000 hertz, bandwidth of 500 hertz. This doesn't show noise, but if you add in noise, there's more chance that with noise, this bandwidth of 500 hertz will lead to errors. That is, we'll get the wrong bits received. There's less chance that the bandwidth with 400 hertz that there'll be errors, because it's more accurate. So in general, the larger the bandwidth, the more accurate our signal can be, and the less errors that less errors will occur. And that applies here as well. In fact, our sinusoid, our square wave, in theory, has an infinite bandwidth, a very large bandwidth, and less chance of errors compared to signals with a smaller bandwidth. So that's our first point, that is, increasing the bandwidth reduces the chance of errors. What we want to cover today is some other impact of our signals on errors and also on data rate. Ignore the bottom diagram for a moment and the question. Let's just focus on the square wave signal. Let's do some quick calculations, ignoring the period and so on. Just look at the signal and the time scale that we have here. So it's shown on here that it goes from 0 up to 0.01 seconds. In other words, this period here is 1 millisecond. So the total period or total duration is 10 milliseconds there. And we're using this signaling scheme where transmit at a high level, +1, represents bit 0, and transmit at level 2, which is a value of a magnitude of -1, bit 1. So if I was using that scheme, then this signal represents the data 0, 1, 0, 1, 0, 1, 0, 1, and so on. Okay. What's the data rate for this signal? How many bits per second can I send with this, or am I transmitting? How many bits per second am I sending? About? I'd like an exact number. Look at the scale. This is 1 millisecond. Okay. All right. How many bits per millisecond am I sending? In 1 millisecond, from the start to here, that's 1 millisecond. There are 2 bits. 1, 2. Okay. So 2 bits in 1 millisecond. Therefore, the answer is 2 bits in 1 millisecond. Therefore, how many bits per second? 2,000 bits per second. So we'd say the data rate Another thing we can talk about, and it will become useful later, we can call this So this is our entire signal. At one level is a single signal element. Okay, this is one signal element. This is the next signal element, and so on. There are multiple elements to this signal. So we can talk about the number of signal elements per second. This is 1, 2, and it's the same in this case. 2,000 bits per second, we have 2,000, I'll call them signal elements per second. The rate at which we send signal elements per second is sometimes called a signal rate. This will become, this terminology will become important later when we compare the second diagram. We're sending 2,000 signal elements per second. Each signal element represents, or each level represents 1 bit here. 2,000 bits per second. Easy. Now, let's try something different. Up until now, we've assumed these simple schemes, that one level corresponds to 1 bit. We don't need to do that. And that's what the second diagram shows. Let's try a different scheme. Where we have 4 different levels. We see here 1, 2, 3, 4. That is, this one is 0.33, minus 0.33, plus 1, minus 1. So we have a signal which we can transmit at one of 4 different levels. I'll write them down. Level 1, and in this example here, the levels are 0.33, minus 0.33, 1, and minus 1. Let's do it. Plus 1. So that's our 4 levels in this case. We don't have to have those exact values. It's just to illustrate having 4 different levels. Now we want to transmit bits. Let's say our sequence of bits I want to send is this random sequence. Just 8 bits. I want to send 8 bits. Focusing on the top scheme first. I would transmit those bits by sending my signal at different levels. The blue. So back to the first scheme, if I want to transmit bit 1, I transmit a signal at level, over there, the top scheme. Bit 1 is transmitted at level 2, which is in fact a magnitude of minus 1. I'm just giving the level a number so I can refer to them. Ignore the, or we want to not refer specifically to the value. So if I want to send a bit 1, I transmit at level 2. If I want to send a bit 0, I send at level 1, whatever the magnitude is. So to transmit this random sequence of 8 bits, I would first, for some duration of time, transmit at level 2, and then at level 1 to represent bit 0, level 2, then 1, 1, 1, 2, 2. And in fact, if I drew the signal, it would look something like this. Level 2 is minus. That is minus 1, plus 1, minus 1, plus 1, plus 1, plus 1, minus 1, minus 1. If I drew the square wave to represent that signal. I just changed the levels when I need to change the transmit different bits. That's using the top or the first scheme that we've described. Now, in the second scheme, we have 4 levels. How do I transmit my random 8 bits using those 4 levels? What can I do? What can I do to transmit this sequence of bits 101, 00011 using this new scheme, the diagram at the bottom, which has 4 levels. What do I do? I need to transmit a signal, yes, and at what level do I transmit first? To represent the first bit or bits, what level do I send at? What level? Well, we need to define what each level represents. In the first scheme, we said that level 1 represents bit 1 and level 2 level 1 bit 0, level 2 bit 1. Let's define a mapping for each level to a sequence of bits. And we don't have to have a single bit. What we can do, for example, there's other variations. If I want to send bits 0, 0, transmit at level 1. Bits 0, 1 at level 2, 1, 0, level 3, and 1, 1, level 4. Okay, so that's a possible mapping. I could do this in a different order if I wanted to. Now, let's look over here what we need to do to transmit this same sequence of bits using our second scheme. Well, now we transmit one signal element for every 2 bits that I want to send. The first 2 bits I want to send are 1, 0. From our scheme it says transmit at level 3. The next 2 bits are also 1, 0, so transmit at level 3. The next 2 bits, 0, 0, level 1, and 1, 1 is level 4. And I could draw that. Level 3, level 3 is minus 0.33, is the magnitude. So if this dashed line is 0, level 3 is minus 0.33, and then again minus 0.33, and then level 1 is plus 0.33, and level 4 is minus 1 down here. All right, where this is 0.33, 0.33 minus 1. That would be the signal using our signaling or signal encoding scheme to transmit this sequence of 8 bits. So we don't have to use one level per 1 bit. We can have more complex schemes. Using this more complex scheme, and which is shown here on the second plot, what's our signal rate first? Now looking at the second plot on the screen, here's our time scale. This is 1 millisecond, 2 milliseconds. How many signal elements do we send per second? How many signal elements do we send per second? In the second, so a signal element is just one level. Okay? How many do we send per second in the second plot? How many are we sending per second? This is just, for those who cannot see from the back, this is 1 millisecond. Okay? 0 to 1 millisecond. How many are we sending per 1 millisecond? How many signal elements? In 1 millisecond? In 1 millisecond, in this time, 2. Therefore, in 1 second, 2,000. Okay? So this is a signal element, this is another signal element, and so on. We have what's called a signal rate of 2,000 signal elements per second. The same as the first one. We see that the levels are the same duration. So it's the same signaling rate as the first one. How many bits per second? What's the data rate? not 2000. What's the data rate? Simply from this diagram. That is, we know that this is one. The units here are seconds, so this is 1 millisecond from 0 up to 0.001. That's 1 millisecond. This is one signal element. This is another. And you could count them if you go up to 1,000 milliseconds. But we see there's two, or simply there's one every half a millisecond. One every half a millisecond, and therefore two every 1 second. That's the same in both of them. How many bits per second? What's our data rate? Look at our signalling scheme, the definition on the right side. How many? We have 2,000 signal elements per second, where a signal element can be one of 4 levels. Each level represents 2 bits. Therefore, one signal element carries 2 bits of data. That is, this represents 2 bits of data, this another 2 bits of data, and another 2 bits. And the same as what we drew over here. This signal element represented 2 bits of data, 2 bits of data, and so on. Here we have 1, 2, 3, 4 signal elements, 8 bits of data. With the top one, we had one signal element representing just 1 bit of data. So the data rate for the second scheme is 4,000 bits per second. Same signalling rate, but with the different schemes, we have a different number of bits per signal element. So, we can send faster with this new scheme. In general, by having more levels that we can transmit at, we could have more bits per level or more bits per signal element, and with the same signal rate, we can increase our data rate. I'm not going to draw it, but if we had a scheme with 8 levels, what's our data rate? Given the same signal rate. 8 levels. 8 levels. Not 8,000. Same signal rate, but 8 different levels. Here we have 4. Initially we had 2. What if we had 8? 6,000. Big Y. With 8 levels, each level would use 3 bits because we have 000, 001, all the way up to 111. There's 8 different values. So each level would represent 3 bits with the same signal rate of 2,000 elements per second. Each element represents 3 bits. 3 times 2,000 would be 6,000 bits per second. Increase the number of levels, increases our data rate. That's a good thing. We want high data rate. So we can use different signalling schemes to increase our data rate. Now, that's the easy part. What's bad about using more levels? Increases our data rate, good. What is bad about it? What is the disadvantage? What do you think the disadvantage is?
I don't understand.
Okay, what do you not understand?
I don't understand why what's different between data rate and signal rate?
Signal rate is, because now we're distinguishing between the signal and the rate at which it changes, it may change between levels. So one level, another level, and so on. So that occurs at some rate. In this case, one level lasts for half a millisecond. Therefore, we can have 2,000 different levels, or a signaling rate of 2,000 signal elements per second. But now we've made it more complex by saying that we don't have to have just two levels. That's what we've done up until now. Now we can say we can have more than two, where each level can represent more than one bit. If we have two levels, then the best we can do is one level represents bit 0, another bit 1. If we have 4 levels as an example, we can have each level representing 2 bits. So now, here's 2 bits, here's another 2 bits, and another 2 bits, and so on. And with a signaling rate of 2,000 elements per second, each element is 2 bits, we get a data rate of 4,000 bits per second. So we now differentiate between the rate at which we change the signal and the rate at which bits are communicated. Remember, our signal just represents bits, in this example at least. Does that make sense?
How can I get the data rate?
The data rate is the signal rate multiplied by the number of bits per signal element or per level. Here we have 1 bit per level or per signal element. And here we have 2 bits per level. 2 bits is represented by each level. The data rate is the signal rate multiplied by the number of bits per level, or bits per element. Level or signal element. 2 times 2,000, 1 times 2,000. With 8 levels, we'll get 3 times 2,000, 6,000. Let's return to the hard part. What's the problem with this? Well, let's do one more example before we return to the hard part. Signal rate is the same. We have the same rate signal, 2,000 per second. Signal elements, SE per second. Signal elements. I want to achieve a data rate of 16 kilobits per second. What do I do? How many levels do I need? My signaling rate is 2,000 elements per second. I want to achieve a data rate of 16 kilobits per second, or 16,000 bits per second. 8 levels. Why 8?
16,000 divided by 2,000.
I don't think it's the correct answer, but you're on the right track. All right, 16 is 16,000 bits per second, 16 kilobits per second. Signal rate of 2,000. We want a data rate of 16,000 bits per second. Therefore, we would need to send 8 bits per signal element. That is, if this is, here's one signal element, this must represent 8 bits, and another 8 bits, and so on. Or we can also say 8 bits per level. And the question is, how many levels? How many levels? That's the number of bits per level. How many levels? If we have 8 bits per level, how many levels do we need? How many different levels do we need? Look at the first case. We had 1 bit per level. We needed 2 levels. 2 bits per level. We needed 4 levels. If we had 3 bits per level, we'd need. If we had 3 bits per level, we would need. If we had 3, we'd need 8. If we have 8 bits per level, we need. Someone just said 2 to the power of 8. Levels. 256 levels. Okay. Because 8 bits per level, we need to be able to represent any sequence of bits. I'm not going to write them all, but the possible combinations you can try. You write all combinations of 0 and 1 for 8-bit length and you get there are 256 values there. So if I want to transmit my sequence, which I've removed from the board, it would be one of these 256, one of the 8-bit sequence I had before. I'll just transmit one signal element. So now if one signal element represents 8 bits, we need 256 different possible levels. 2 to the power of 8 possible levels. And then we could achieve a data rate of 16 kilobits per second. Increasing the number of levels increases our data rate, given the same signal rate. Don't need this. I'll leave that. Now, that's a good thing about using more levels. We get higher data rate. The bad thing is that when we have noise, we will get more errors. That is, comparing our 2 signals again, with the bottom signal, where we have more levels, there are more chance of errors. Let's try and explain why. Let's first focus on the top scheme. In the top scheme, let's remove this. What causes an error in the top scheme? How much noise do we need for an error to occur with the top scheme? What's the magnitude of the noise? Can anyone put a number to it? The magnitude of the noise needed such that the transmitted signal in the top scheme will result in an error at the receiver. 1. Let's see why. Now let's look at the absolute values just so we can put some numbers to this. Level 1 is a +1. At the top, this is a transmitter, +1, level 2 is -1. An error occurs when the receiver receives a signal and they think it's the wrong level. That is, let's say we transmit at level 1, that is, the magnitude is +1, 1.0, that's what's transmitted. We go back. This is the transmitted signal. We add noise to it. There's noise, okay? And the noise can vary. There may be spikes and so on, like we have here. We add noise, which changes the received value. Transmitted at +1, plus the noise and attenuation. In this example, it's received It's going up and down, but it's about, on average here, 0.33 or 0.3. 0.4, 0.3, doesn't matter. Okay, that's the received value. So let's consider an example where if we transmit at level 1, +1, and now let's look at different possible received values. So assume there's some noise. And if the receiver receives at the value 0.9, what does the receiver do? Do we have a bit error? No. What the receiver does is takes the received value, or the simplest thing we can think that the receiver does is compares the received value with the expected transmitted values. Either +1 was transmitted or -1. And it compares and finds the closest match. What's the closest match between 0.9 and the two possible transmitted values? It's +1. It's closer to this than this one. Therefore, the receiver assumes, even though I received not one of the two transmitted values, but a different value, it assumes that the one transmitted was the closest, which would be +1. And if we assume +1 was transmitted, we assume what's received is bit 0. What was transmitted? Well, we transmitted level 1, which in fact was bit 0. We transmitted bit 0 at +1. We receive at +0.9. Receiver assumes bit 0. That's correct. That's good. We transmit and receive the same bit. Another case. Receive at a level of 0.5. What bit does the receiver think that they received? Or which one is it closest to, level 1 or 2? Level 1, it's still closer to this one. Close to level 1, therefore bit 0 received, right here. Bit 0 received, bit 0 transmitted, that's fine. Receive 0.1. Closest to level 1 or 2? Still level 1, okay? Therefore 0, fine. Receive -0.1. Which one is it closest to? Now we're closer to level 2. Okay, -0.1, closer to level 2. Therefore assume level 2 was transmitted, bit 1 was transmitted. The receiver thinks bit 1 was transmitted. There's our bit error. Bit 0 was transmitted, bit 1 is received. That's wrong. That's what we don't want to happen. And I think you'll see the, okay, -0.5 will also be a bit error. We have two levels. The midpoint is 0. That is, if we transmit +1, if the received signal is less than 0, we'll get a bit error. And the opposite way, if we transmit -1, if the received signal is greater than 0, we'd get a bit error. That is, the noise has to be a magnitude greater than 1 to cause an error. An error will happen if the noise magnitude is greater than 1. So if we transmit our signal and our noise is large enough, in this case greater than a value of 1, we'll get a bit error with our scheme. Okay, what if we receive 0? What are we going to do? Well, we need to have a rule that says, for example, if we need to make a decision one way or the other. If it's greater than or equal to 0, assume it's level 1. If it's less than 0, assume level 2. So we need to decide either way. And that rule as to how you decide must be defined by the transmitter and known by the receiver. So you can think the receiver knows anything in this case which is greater than and equal to 0, consider as level 1. anything that is less than 0, consider as level 2. Okay, so we need to define a cutoff somewhere and go one of the two ways. With this scheme, if the noise is larger than a magnitude of 1, we get bit errors. Let's try the second scheme and see how much noise is likely to cause a bit error. Note with the second scheme we have 4 levels, +1, plus 0.33, minus 0.33, minus 1. Let's say we transmit at level 2 as an example, which actually is the bits, level 2 corresponds to the bits 0, 1. That's what's transmitted. And the magnitude was plus 0.33. Now we receive a signal, it has some noise in it, it changes the magnitude of the received signal. For example, let's say we receive at 0.4. What happens? Which level does the receiver think was transmitted? Level 2. Because if we compare 0.4 to the 4 possible values, we look which one's closest. Well, 0.33 is the closest to 0.4. 1 is further away, and of course minus 0.33 is further away. So the closest level is level 2. So it assumes level 2, and therefore it assumes the bits 0, 1 were received. 0, 1 were transmitted, 0, 1 received, everything's okay. So what the receiver does is take the received signal and compares it to the expected transmitted signals and finds the closest. 0.5 was received. Which one's closer? Level 1, 2, 3 or 4? Compare 0.5 to 0.33 and 1. 2, okay? It's a difference of 0.17. Still level 2. Therefore, still the bits received are level 2 bits, which is 0, 1. Everything's okay. 0.7. Level 1. Because the difference between level 1 and 0.7 is 0.3. The difference between 0.7 and 0.33 is 0.37. That is, it's closer to level 1 than level 2. And therefore the bits, if you look on the other side, the bits received 0, 0. Bit error. Something's gone wrong. Okay. And we could keep going and look at other cases. For example, 0.9 minus 1.3 and so on, we could look at different values. In this case, if we transmit at level 2, how big does the noise need to be to get an error? The noise needs to be larger than some value. What should it be in this case to produce an error if I transmit at 0.2, at level 2, or transmit at 0.33? How big does the noise need to be to get the wrong bits received? Again? 0.33. Why? Well, look at the midpoints of each of the levels. The midpoint of these two is 0.66. Here is 0. Here, 0.66. So if we transmit at this level, if we go down by 0.33 or more than 0.33, would end up in level 3. If we go up by more than 0.33, we'd end up in level 1. So if the noise is greater than 0.33 in this case, we get a bit error. Whereas in the first case, it had to be larger. That is, the noise need to be greater than a magnitude of 1. The point here is that the more levels we have, with the same amount of noise, we've got more chance of bit errors. For example, if the noise was 0.5, in the first scheme, if the noise was 0.5, there will be no errors. But in the second scheme, if the noise is 0.5, there will be errors. So the more levels we have, the more chance of bit errors when we have noise in the system. And that's the negative or the disadvantage of the second scheme. It gives us a higher data rate, but when we have noise, we get more bit errors. And in fact, that reduces the rate at which we can transfer our real data. If the noise is all right, this is the transmitter value. If the noise was such that the received value was 0, then again we need to make a decision. Do we treat it as 3 or 2? So we'd need to define, okay, level 1 is greater than or equal to 0.66. Level 2 is less than 0.66 and greater than or equal to 0. Level 3 was less than 0 and greater than or equal to 0.66, and level 4 is less than 0.66. We need to divide that space between those 4 levels. So we need to have a cut-off somewhere. If it's exactly one of the values, then we need to define which of the 2 levels it corresponds to. Any questions on the concepts here? More noise, more levels with the same amount of noise, we get more bit errors. More levels means more bits per signal element, more bits per second. Yep.
How can I get noise?
This noise greater than 0.33. If I transmit at plus 0.33, there will be an error if the received signal is anywhere between if the received signal is, let's say, greater than or equal to 0.66, there'll be an error, assuming we transmit at 0.33, and if the received signal is less than 0, there'll be an error. If I transmit at 0.33, if the receive is greater than this, that is, it takes us into this level, there's an error, or if it takes us in this level, there's also an error. So if this varies by plus or minus 0.33, there'll be an error. That is, and what causes the variation? Noise. The transmitted signal, all right, we have attenuation, but the noise causes the variation. If the noise is greater than 0.33, we get an error, just if we transmit at level 2. Does that answer your question? The absolute values, the 0.33, the 1 and so on.
Be the TX, right?
Yes, that's only if I transmit at level 2. Whenever I transmit level 2, which is really transmitting the bits 0, 1, I send this signal. This is 0.33. Okay? 0.33. See, I transmit a signal at this level. Of course, it's received at a different level because of noise. If the received value is greater than 0.66, the receiver will think it's level 1. If it's less than 0, the receiver will think it's level 3 or even level 4. So anything outside of this range is an error. And that's, we see 0.33 is the difference between here and here, and also between here and here. Of course, the exact numbers are not important here. It's the concept of more levels, more errors. More levels, higher data rate. So that's the trade-off we need to deal with. Any questions before we move back to our lecture notes and on the next topic? Any questions? A lot. Well, you'll go and watch the video since you've just missed the major part of the lecture. It won't help much because most of it's on the board today. And if we had 8 levels instead of our 4, then there'd be 8, we'd have 8 different levels between plus and minus 1, and a smaller amount of noise could still cause an error, because we only have to shift a little bit to get the wrong level. We divide the space into 8 different bands or 8 different sections. With 2 levels, we have 1 and 1. With 3 levels, we see we've divided it into 4 different bands. If the received signal is in one of the other areas, we get an error. It's important to understand that concept because it comes up in our next last part of the lecture, which is about capacity. What we want to do now is finish up on this topic with a look at some theorems that relate data rate, which I've removed, with other characteristics of our signal, in particular bandwidth. We've done some calculations. Yesterday and last week we did calculations where we saw a particular signal and we calculated a data rate. What we're going to go through is 2 theorems that brings these concepts together and relates bandwidth and data rate as well as 2 or 3 other factors. And this is about finding what is the maximum data rate, that is the capacity, a maximum data rate, that we can send our data through some given communication channel. A channel, a medium or a link. Okay? From one computer to another, we have a channel. How fast can we send our data? That is, what is the data rate or the capacity C in bits per second? We want to know that. People have done analysis in the past and shown that it's related or proportional to the bandwidth of our channel. So we can send signals of a particular range of frequencies through our channel, that is with some bandwidth, and the capacity is related to the bandwidth, but also other factors like the number of levels that we just saw, noise and errors. We're going through 2 theoretical models. One's called Nitrous Capacity, or the Nyquist equation, and Shannon capacity, created by Nyquist, Mr. Nyquist and Mr. Shannon. And in fact, some other people contributed as well. Let's first look at Nyquist capacity. Let's make some space. Let's assume we have a channel. We want to transmit from A to B. We have a link. We have a link from A to B, a communications channel. We can send a signal through that link. Calling it B is a bad... Let's call it 1 and 2. You'll see why in a moment. Between 1 and 2, we have a link, and that link, the transmission media and the transmitter, limits the bandwidth of the signals that can flow through the link. And the bandwidth that can pass through that link has a value B hertz. Okay? what we want to find out is how fast can we send our bits if we have a bandwidth of B hertz? What's the capacity C? Nyquist did some analysis and come up with the point that if we have a bandwidth of B, the highest rate at which we can send signal is twice the bandwidth. That's our signal rate. So it says if we have a bandwidth of B, the signal rate, the highest signal rate, is 2B. This is assuming that there's no noise. Okay? When everyone stops talking, when the air conditioners are turned off, no one's moving, there's always some background noise. And in electronics, there's always some thermal noise. In real life, there is always some noise in our communication system. But to make the analysis easier, Nyquist assumed that there was no noise. In a perfect environment, if there was no noise, he says that the signal rate would be twice the bandwidth. But there's another factor involved, and that's what we went through. By increasing the number of levels we have, we can send more bits per signal element. So the data rate, or the maximum data rate, and referred to as C in this equation, the capacity, is related to the signal rate. And in our case, what did we do? I had an equation before. I had data rate equals signal rate times by what? What did I write down? I'm sure someone copied it down. Before, I had data rate equals signal rate times by what? Number of bits per level. Data rate equals signal rate times by the number of bits per level, either 1 bit per level or 2 bits per level. And that's what this part is, this log 2 of m. If there are m levels, if there are 2 levels, it's multiplied by 1. If there are 4 levels, it's 2. If there are 8 levels, it's 3. That is log in base 2 of the number of levels m. So m is the number of levels for our signal. Log in base 2 of m is the number of bits per level. Therefore, the data rate is the signal rate times by the number of bits per level. And that's what the Nyquist capacity equation tells us. So if we know a bandwidth of our channel, 1000 hertz as an example, and we're using this signalling scheme, what's the data rate? What's the maximum data rate? My bandwidth is 1000 hertz, and we're using the first signalling scheme. What's the maximum data rate? That is, we're using the top one. (2000 bits per second). Simply, bandwidth is 1000. 2 times 1000 is 2000. And here, m, the number of levels is 2. Log base 2 of 2 is 1. So we get 2 times 1000 times 1. We get a data rate with this scheme of 2000 bits per second. With this scheme, same bandwidth, 1000 times by 2, we get 2000. And the number of levels here is 4. Log base 2 of 4 equals 2, because we have 2 bits per level. So we get a data rate of 2 times 1000, which is 2000, times by 2, 4000 bits per second. And we did that calculation before. Increasing the number of levels increases our data rate. Increasing our bandwidth increases our data rate. And that's shown, sorry, we've lost it, in Nyquist's capacity equation. Capacity, or maximum data rate, is 2 times the bandwidth of our channel log base 2 of the number of levels for our signal that we send. Assuming no noise. We know there is noise in practice, but if we make the assumption of no noise, this holds. We're not going to try and prove this. We've seen some examples that demonstrate it. We can use it to evaluate approximately what the data rate we can achieve in some channels. From the equation, of course, we see you make the bandwidth bigger, you make the data rate bigger. Bandwidth goes up, data rate goes up. Also, we see if you increase M, if you increase the number of signal levels from 2 up to 4, the data rate goes up. That's the good thing. To make your data rate higher, increase the bandwidth and/or increase the number of signal levels. What the equation doesn't show, we know already though, increasing the bandwidth increases our cost. That's one thing. Also, and we saw from the previous example, increasing the number of levels, and the point that's made here, increases the errors when we have noise. If we do have noise, and we always do, the more levels we have, the more errors we can have. That's not captured in the equation because it assumes no noise. So in theory, if there was no noise, all we do, if we want 1 gigabit per second and we have a bandwidth of 1000 hertz, we just keep making M larger and larger such that we get the data rate we require. But we know that that's not practical in real life because of the errors that will arise. There are practical limits of M, the number of levels. It depends in some cases on the receiver hardware as well, what it can interpret. Let's do a simple calculation. And in this calculation with a telephone line, first assume we have the simplest case. What's the lowest reasonable value of M? What's the lowest number of levels that we could use?
1,
2. We need 2 levels because we need to represent 2 different bits, 0 and 1. Assuming M equals 2, find the data rate of your telephone line, the maximum data rate. If we have 2 levels, how many bits per second can you send across your telephone line? Again, 6,200. 6,200. Simply, we have a bandwidth of 3,100 hertz. Nyquist capacity equation is 2 times the bandwidth log base 2 of M. 2 times 3,100 times by log of 2 is what? Log of 2 in base 2 in base 2. Log of 2 in base 2 is 1. Okay. And the units of the bandwidth are in hertz. The units of capacity, bits per second. if we're using, and this is a realistic value, your telephone line for voice calls transmits signals at a bandwidth of about 3,100 hertz, your home telephone line. If we're using a signalling scheme which has just two levels, like this very simple one, the maximum speed at which we can send our data is 6,200 bits per second. Simply using Nyquist's equation. I asked you yesterday who had home internet, ADSL internet. Several of you, or some of you have ADSL at home. Okay. What about before ADSL? What did you have at home for internet access? Did anyone have internet access before ADSL? Dial-up modems, anyone remember them? They make that squawking noise when you dial up, okay? Could you talk on the phone as well as use the internet at the same time? No, you just either talk or use the internet with a dial-up modem. How fast? Anyone remember? 56 is a common number that you would have heard, 56 kilobits per second. You had a modem, connect to the telephone line. Telephone line, when you talk, transmits a signal with a bandwidth of 3,100 hertz. And what your dial-up modem did was, instead of sending your voice, it sends bits encoded as a signal across that with a bandwidth of 3,100 hertz. How many signal levels did your modem use to get a data rate of 56 kilobits per second? Typical data rate you could achieve was 56 kilobits per second. The bandwidth is 3,100. Nyquist capacity gives us a relationship between the two. The unknown is M. How many signal levels do you need? What's the value of M? Try and calculate the value of M. Data rate C is 56 kilobits per second, 56,000 bits per second. Bandwidth is 3,100, same as this question. How many signal levels do we need? And this is the capability of your modem. That 56 kilobit per second modem transmitted a signal with many different levels. How many? You just rearrange our equation and find M. Anyone found an appropriate value of M yet? You know how to use that calculator? Where's the answer then? 56? I gave you 56. Anyone? Yeah, I want M. You forgot, okay. That won't help in the exam. Start writing. Try. I've given you the start. Log base 2 of M. Just rearrange the Nyquist equation. You know B, you know C. Want to find M. 2 to the power of 9. That sounds close. 2 to the power of 9.03 something. That sounds close, but wrong. 4. That's way off. Let's do it. C is 56,000 bits per second. B is 3,100. 2 times B is 6,200. And we get here 56,000 divided by 6,000, 9.03, correct? 9.03 something. So how many levels do we need to get this capacity? What about M? What should M be? Log base 2. No. Wrong direction. Log base 2 of M equals 9.03. What value of M should you use? 2 to the power of 9. What's 2 to the power of 9? Let's try. All right. In theory, the mathematics, it should be M equals 2 to the power of 9.03. But you need to be careful. When we talk about levels and bits, we have to have an integer number. That is either 9 bits per level or 10 bits per level. You can't have 9.03 bits per level. There's no such thing as a 0.03 of a bit. Let's try the 2. Let's first try M equal to 9. If M was 9, we know the bandwidth is 3,100. What capacity do we get? 2 times 3,100. Sorry, if M was 2 to the power of 9, we had log base 2 of M equals 9.03. If M equals 2 to the power of 9, which is 512, log base 2 of 2 to the power of 9 equals 6,200 times by 9 gives us what? I think 55.6 kilobits per second, or close to. Is that correct? 55.8. Which is close enough to our 56 kilobits per second. When someone says in their modem it's 56 kilobits per second, well, 55.8 is probably what they mean. Okay? 10 would give you, what is it, 62 kilobits per second. So we know that your modem, your dial-up modem, had at least 9 levels, probably 9. If there were some overheads, for example, maybe it had to go higher. But I think it was 9. Okay, your modem, dial-up modem, only supported 56 kilobits per second. Why couldn't it go faster? Why couldn't your dial-up internet be faster? If you were to design a modem, what would you do to make it faster? You'd dial-up internet. Increase the bandwidth is one thing. What about another approach? You're going too far ahead. What about your equation? What would you do to make the bandwidth larger? The data rate larger? Yes, make the bandwidth larger, or increase the number of levels. So change the implementation of your modem so your signal uses not 512 levels, but 1,024 levels, for example. That would increase the data rate. But we know the more levels, the more chance of errors. So the technology at that point in time was that using 9 levels as, using 512 levels was about the best that they could do for the receiver. This all assumes no noise. Shannon improved upon this analysis under the condition that there is noise. And in the last 5 minutes, let's go through Shannon capacity, a different approach. Shannon takes into account the fact that there is noise. And the concept is the more noise, the lower the data rate. It's the same in this room. The more people that talk, the less information that I get to you. Similar, if on the microphone, my signal power increases and the more information gets to you. So Shannon has this ratio, or uses the ratio of the signal to noise at the receiver. If the signal to noise ratio increases, we can get more data rate. That is, the less noise, the more data. The higher the signal power, the more data. And we also, of course, it depends upon bandwidth. So Shannon says that the capacity of our channel is equal to the bandwidth multiplied by log base 2 of 1 plus the signal to noise ratio. So we have our source sending to a destination. Bandwidth, let's say, is 10 megahertz. And we receive a signal with some power level. Let's say 511 milliwatts. Okay? That's the received signal. I can measure the power level of the received signal. It's 511 milliwatts. But there's also some noise. And the receiver receives some noise as well. Let's say it's 2 milliwatts. So there's a little bit of noise and the signal is very strong. So the signal to noise ratio is 511. Why did I say 2? Doesn't matter. Let's make it easier so I can divide. 512 divided by 2. The ratio between the signal strength at the receiver and the noise strength at the receiver. Just the division. Signal divided by noise. Again, I've used the wrong values, but that's okay. Which is 256. The signal to noise ratio is 256. Or the signal is 256 times stronger than the noise. And from our equation, the capacity equals the bandwidth, 10 million, times by log base 2 of 1 plus the signal to noise ratio. 1 plus 256 is 257. Log of 257 is approximately 8. It's a little bit more than 8 point something. You can use your calculator. It's about 8. 8 times 10 million is 80 megabits per second. With the signal strength known at the receiver and the noise level known at the receiver, and given a bandwidth, we can determine the maximum capacity or the maximum data rate according to this, where the signal to noise ratio is simply the signal strength divided by the noise. If we increase the signal strength, if S goes up, the capacity will go up. If we increase the bandwidth, the capacity will go up. If we increase the noise, capacity will go down. Okay? The more noise, the less information gets communicated. And you can see that in the equation. We're almost out of time. What you're going to do in the quiz is practice the Shannon and Nyquist capacity equations with there's 3 or 4 questions, easy. But the thing you need to do before the quiz, and this is your homework, is that the signal to noise ratio, this is in an absolute value. But often people refer to specify in a logarithmic value, decibels. You need to go and refresh your memory. This is in one of the handouts at the start of the semester, which defines, or for us, what is a decibel. It's a ratio between two power levels, but a logarithmic ratio. You take the logarithm multiplied by 10. What you're going to do before the lecture next week is to learn how to convert from the absolute value to decibels, because you need that to answer the quiz questions. Okay? You need to understand decibels for the quiz question. So read, there's only about half a page or 1 page about decibels. That's all you need to read. Then attempt the quiz.